part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss the magnetic vector potential. In the previous two lectures, we discussed the BocaPhysics law, working through a few examples, and then we also talked about Ampere's circular law. So let me write those down on the board. The BocaPhysics law, and I've just written down the expression if you have a volume current density. They're analogous expressions for a surface current density and also a line current. Okay, so we also had Ampere's law in differential form. Curl of the magnetic field is equal to mu naught times the volume current density, and in integral form, the line integral of the magnetic field around a closed path is equal to mu naught times the amount of current enclosed by that path. Now, during the course of this analysis, we determined a couple of expressions, namely that the magnetic field is divergence-free. As it turns out, this holds not only for static fields, but also for time-varying fields as well. So this is always the case. And we also determined that the divergence of the volume current density is equal to 0. However, as it turns out, this only holds in magnetostatics. Back when we were studying electric fields is a vector quantity, and it was convenient to introduce the electric potential. Electric field is equal to minus the gradient of the potential, and in that way it opened up a whole bunch of tools for analyzing certain systems. So we spent a lot of time working on boundary value problems, basically because the curl of the electric field vanishes in statics, electrostatics. That means we can write electric field as the gradient of some scalar, and it's convenient here to take that as minus the gradient of the potential. Now, it would be nice if there was some potential that we could choose for magnetic fields such that it simplified the problem, okay? So if I look up here, this always holds, so let's say that we assume that the magnetic field can be written as the curl of some other vector. Okay, then this condition will always be satisfied. So I'm going to call this the magnetic vector potential. However, as you might notice right off the bat, this is a vector quantity. It's not a scalar. And so that's going to make things a little bit difficult. And as we'll see, the magnetic vector potential is not nearly as useful as the electric potential. Certainly not at this stage of the game. Where magnetic vector potential comes in useful is if you're doing electromagnetic radiation or if you're studying eddies, then that's a neat quantity to use. But for now, we're really just introducing this quantity, and we're going to work through a few examples to see how it behaves, okay? So let's flesh this out a little bit better. I'm going to plug this into Ampere's law. So I'll have the curl of the magnetic vector potential is equal to mu naught J. If you consult a table of vector identities, I can write this in a somewhat different form. This is the gradient of the divergence minus Laplacian is equal to mu naught J. I have a certain amount of freedom in choosing A. Back in electrostatics, V was defined to within an arbitrary constant. So if you were careful when you talk about electric potential, you'd always say, well, it's a potential with respect to some point in space. Oftentimes it's infinity, Sometimes if you have an infinite charge distribution, you choose some arbitrary point in space. But the point is, V is defined to within a constant. So there's an ambiguity in the definition of the magnetic vector potential as well. So to make life easier on myself, I'm going to choose the divergence of A equaling 0. Okay? So, this is the equation I aim to solve. Laplacian of the magnetic vector potential is equal to minus mu naught times the volume current density. Now, again, going back to electrostatics, it is also true that the divergence of E is equal to volume charge density over epsilon naught, and combining these two, you have the Laplacian is equal to minus the volume charge density over epsilon naught. If I compare these two expressions, the form's the same, except now the Laplacian's operating on a vector as opposed to scalar quantity. So we want to think of this as it's safe, really, to think of this in Cartesian coordinates for the time being, for the sake of this argument. The potential, the electric potential, written in integral form is 1 over 4 pi epsilon naught volume integral over the volume charge density over the magnitude of the separation vector. So by analogy, I can write down A is equal to mu naught over 4 pi times the volume integral of the volume current density over the magnitude of the separation vector. If it feels like, or if you're thinking that maybe we played a little bit fast and was just plugging in numbers, I could derive this expression a different way and start with the Biot-Savart law. And I guess I'm not going to rewrite it again. Let me just write out the integrand. And this is equal to minus the volume current density crossed into the gradient of the separation vector, because minus sign comes in because we take the gradient. This is minus of this, okay? Now, once again, I'm going to use another vector identity. And this time we're going to use the fact that the curl of the product of a scalar and a vector is equal to the scalar times the curl of the vector minus the vector crossed into the gradient of the scalar. By comparing this with this expression up here, So I can replace this using this relation here. So therefore, this term goes to 0. Why? Because we're taking the curl with respect to unprimed coordinates. J, the falling current density, is a function of prime coordinates, so that's just going to go to 0. So therefore, we're replacing this minus J cross curl of 1 over separation vector by curl of J over separation vector. Because this curl operates only on unprimed coordinates, I can pull it out of the integral. And you see, I can identify that as my magnetic vector potential. Okay? There's also magnetic scalar potential, which I will mention briefly in a different lecture, and as it turns out, that is even less useful than the magnetic vector potential is. Okay? So as I mentioned, I'm going to work through some examples. I'll work through 3. We're going to look at an infinite line current carrying ring, and we're going to determine the magnetic vector potential at arbitrary points, not just along the axis. And then we'll also look at the field due to magnetic vector potential due to a sphere that bears surface charge, okay? And it's rotating. Okay, so let me erase this. And here are now the vector potentials for both surface current densities and also for line currents. The first problem I'm going to tackle is that of an infinitely long wire. That carries current I. And I'm going to determine the magnetic vector potential here. And I'll assume that this is lying along the z-axis. Now your first inclination might be, well, I'll just plug it into this expression and do the math. However, just as with the electrostatic potential, you could not use these expressions if you had an infinite charge distribution. You can't use these expressions if you have an infinite current distribution. This goes off to infinity, so this integral is going to blow up. And as before, when I mentioned the defect in these expressions, it's not really a defect per se, because there is no such thing as an infinitely long line charge, and nor is there an infinitely long wire. They're merely textbook approximations. Okay. So with that being said, what do? I mean, I want to figure out what the magnetic vector potential is. It certainly exists for this. So how do I tackle it? Well, I'm going to write down what you know. And what you know about a very long wire is that it has a certain magnetic field, U naught I over 2 pi s, and in a circumferential direction. So this is kind of analogous to the situation with electric fields, because when you looked at the line charge, well, we calculated the electric field first, and then integrated that to determine what the electrostatic potential was. So I'm going to take a similar approach to figuring out what the magnetic vector potential is here. I'm going to make use of the fact that the curl of the magnetic vector potential is equal to the magnetic field. Now, I'm just going to write out the one set of terms corresponding to phi. So in other words, we'll write this as, take that as a phi component, because it's going to be apparent that there's only going to be a phi component from the curl of A. What you'll notice with many of these problems, it is often the case that the magnetic vector potential lies in the same direction as the current. So that's going to be the case here as well. There's no z dependence here. And we just integrate this az, therefore, is equal to mu naught I over 2 pi natural log of s plus some constant. And I'll pick my constant such that A vanishes at some arbitrary point in space. So we'll say mu naught I over 2 pi natural log, and I'm going to leave out the minus sign there, of s over some, I'll say some reference, okay? And that's the magnetic vector potential due to an infinitely long wire. Now, if you had a finite length wire, you could immediately use this expression here. There's no problem with it. It's just for infinite distributions. If you're looking at an infinite current sheet, for instance, you can't use this expression here. You have to follow a similar approach to solving that problem, okay? Well, clearly the curl vanishes. There's no dependence on phi. There's no dependence on z either. Only dependence on s, and it is pointing in the z direction, in the same direction as the current. So curl of A definitely equals a magnetic field. Does the divergence of A vanish? Yeah, because of this form. So let's consider another example. Let's suppose instead of having a thin wire, you had a wire of dimension or radius r. And I want to figure out, again, what is the magnetic vector potential due to this wire. Outside the wire, it just goes to mu naught I over 2 pi s. Inside, however, is this form mu naught times j naught, where j naught represents the uniform volume charge density times s over 2. Now, it's sometimes more convenient to express it in the current, so this is mu naught I s over 2 pi r squared. Okay, So now I want to figure out what is the magnetic vector potential due to the current and inside. So again, using the same procedure as before, you just integrate this. And plus some constant. Well, this time I'm going to choose my constants such that A vanishes at S equals R. So therefore, I can choose my constant such that the magnetic vector potential is minus mu naught I over 4 pi r squared times s squared minus r squared vanishes at the surface. And this is inside. Outside, of course, we'll have the same expression as before. And I'll choose my reference point to be at the radius r. Okay? So these both vanish at s equals r. This one remains finite inside, and this also holds in the outside region. Okay? The next example I'll work through is of a current carrying ring. Assume that this current carrying ring lies in the xy plane and it's of radius r. I want to use this expression or one of these expressions to determine what the magnetic vector potential is, and not just along the z-axis, but at any arbitrary point in space. When we went into, we were talking about B of Savart law, we determined the magnetic field due to a current carrying ring, but only along the z-axis, so that was limited. Now we're going to come up with an expression that applies everywhere. Okay, so this is a line current, therefore we use that expression. And I need to write down what the line element looks like. Use cylindrical coordinates, minus r sine phi prime d phi prime in the x direction, plus r cosine phi prime d phi prime in the y direction. R, our field point, we'll take to be at s cosine phi in the x direction, plus s sine phi in the y direction, plus z curve. R prime is equal to R cosine phi prime, x direction, plus R sine phi prime, y direction. Whenever you're tackling any of these kinds of problems, if you can make use of the symmetry of the problem, by all means do it. Just by looking at this, it's symmetric about the z-axis, so there can't be any dependence on phi. So why not evaluate this integral at phi equals 0? therefore I can write my field point as S in the x direction plus Z in the Z direction. This is the square root, the sum of the squares, so we have square of S minus R cosine phi prime plus R squared sine squared phi prime plus Z squared. I'm going to multiply this out. And that's equal to a square root of S squared minus 2SR cosine phi prime plus R squared cosine squared phi prime plus R squared sine squared phi prime plus Z squared. Well, you see you've got two terms that have R squared in common, and it's cosine squared plus sine squared, which is just equal to 1. I'm just going to go ahead and erase that. Combining the two will wind up with just an R squared and then, of course, Z squared as well. Here we're going to integrate from 0 to 2 pi. The first term, the term that's in the x direction, is going to integrate to 0 because you'll wind up with the square root of something plus something plus something and a cosine phi prime, and that'll be evaluated from 0 to 2 pi, which will go to 0. So that term drops out. We're just left with the second one. And there's your answer. This is an elliptic integral, and I'm aware of that most of you, or many of you, probably haven't worked on elliptic integrals yet. And I could just leave it there, but I'm going to go ahead and flesh this out a little bit better. So if you don't know what an elliptic integral is, let me write it down. These are called complete elliptic integrals of the first and second kind. The reason why they're called elliptic integrals is because you can use this expression to determine the arc length of an ellipse. A lot of times students will take math physics, and for some reason they don't ever get to elliptic integrals, and of course you're going to run across problems in graduate level physics that involve this, and when you do, it might be a little frustrating. Think, wait a second, I took math physics and we didn't talk about it. So I'm going to talk about this problem right now, and even though this is technically speaking, more of a graduate level electromagnetism problem, I'm going to go through and get this expression written in the terms of these two quantities here, okay? So, if you look at we got cosine phi prime inside the radical, but I've got a sine squared phi there. So your first inclination might be, you're going to make use of a trigonometric identity. First inclination might be to choose 2 sine squared phi prime over 2 is equal to 1 minus cosine phi prime. And that might not be a bad idea. Well, it's obviously converting a cosine phi over to sine squared phi. But if you attempt to do this, you will not be able to get this expression into that form. As it turns out, you have to make another transformation. You have to make a substitution here. A substitution. And we'll say that cosine phi prime is equal to 2 sine squared alpha minus 1. Phi prime is equal to pi plus 2 alpha, and consequently d phi prime is equal to 2 d alpha. Now, if you look at this, it might not be immediately obvious, it probably won't be, that you do have to make a substitution of variables. And by setting phi prime equal to pi plus 2 alpha some other angle, then I can write d phi prime is equal to 2d alpha, and therefore cosine phi prime is equal to 2 sine squared alpha minus 1. This is the kind of problem that you can, that stumps you. You might think you're on the right track, which, you know, if you tried to plug in that trigonometric identity, that was sort of on the right track. But as it turns out, you need to make this other substitution as well, and by that way, you'll be able to get this into the proper form, okay? So I'm going to substitute in alpha for the phi prime. I'm also going to make a note before I press on, I might as well do that right now, that I can, it's the same thing as just integrating from 0 to pi times 2. So that takes care of one of the 2's in the denominator. Okay, so I'm just going to write the integral, leave all that other stuff out front for the time being. And therefore, if the integral, instead of going from 0 to pi, it'll go from 0 to pi over 2. And I'll have a factor of 2 out in front because of d phi prime is equal to d alpha, okay? I'm going to rewrite this in the denominator. Now I have 2 times pi over 2, 2 sine squared alpha minus 1, all over square root of s squared plus 2sr plus r squared plus c squared minus 4sr sine squared alpha. Since I'm running out of room, I'm just going to erase this here and replace these first, actually these 4 terms, or 3 terms rather, by s plus r squared. Okay? Now I have to make another assumption. I'm going to multiply the integral by k squared over 2. And if I do that, I have to also multiply it by 2 over k squared. And I'll leave this 2 out front here so I don't lose track of it. Okay, so basically I just multiply by 1, 2 over k squared over 2, and I'm also going to add 0. So I can add 0 by adding a 1 and a minus 1. Now if you're flummoxed as to how I knew to do this, well, it requires some playing around and experience with handling these kinds of problems. This is why this kind of a homework problem can really stump you, and like I said, if you just try to plug in that trigonometric identity and you keep getting the wrong answer, the wrong form of it, you'll think, gee, maybe I must have made some mistake somewhere. At that stage of the game, you didn't. It's just that you have to make this substitution as well, and also multiply and divide. So there is definitely a trick to solving this one. Okay, so I'm going to divide, separate the terms out accordingly. Oh, and let me call k squared, let me set that equal to 4s r over square root of, or rather over s plus r squared plus z squared. And unfortunately, I'm going to have to erase some more of this because I am running out of room. It's convenient here to divide through by s plus r squared plus z squared. Take the square root of that, so 1 over Okay, so what I did here was I replaced, I divided the bottom through by s plus r squared plus z squared. So this first term will be 1, and then over here we'll have 4sr over this quantity, so I'm calling that k squared. And pull that out. This is where I have an extra factor out front here. Again, I just added 0 here, just adding 1 and subtracting 1 from it. And then I also multiplied through everything by 2 over k squared, but I'm multiplying through by k squared over 2, so that's equal to 1 as well. Now I finally have my integral in a form so that I can identify this with this. You see, this first term here is the k integral. It's the first complete elliptic interval. So this is 1 minus k squared over 2 times k, function k. Second term, you see I have a 1 minus k squared sine squared alpha in the numerator and a square root of 1 minus k squared sine squared alpha in the denominator. So that's basically square root of 1 minus k squared sine squared alpha. So I'll just write this as minus ek. Okay, I'm not quite done yet. I need to take account of all this out front. So I'll write A is equal to y mu naught I r over 2 pi. We have 4 over k squared. And there's your integral. However, I do want to clean this up a little bit, so delete this on the right hand side. I'll just leave it up for another minute before getting rid of it. Okay. Okay. So I've just written 4SR as a product of 2 square roots, square root of 4SR, square root of 4SR, and I've divided S plus R squared, actually R squared should be out there, S plus R squared plus Z squared all over square root of S plus R squared plus Z squared, so you wind up with square root of S plus R squared plus Z squared. Okay, so if I look at this, that's equal to 1 over the square root of little k. And look, this 2 will cancel with this square root of 4, which is just 2. This r will cancel out part of this, so we'll end up with y mu naught I over pi. Start a little bit low to the left from one. And there's your answer. Mu naught I over pi, square root of radius over s, 1 over little k, bracket, 1 minus little k squared over 2, complete elliptic integral of the first kind minus complete elliptic integral of the second time. Now, we just evaluated this at phi is equal to 0, but generalizing it to any point, because I know that vector potential is going to behave the same way, I can replace that by phi caret. Okay? Now, this is a difficult problem. It's graduate level. It's difficult because you have to kind of have a little bit of insight into how these problems work to choose a substitution properly. And normally most people don't cover this in undergraduate EM. I'm covering it now because when you get on to graduate school, it is possible that you may not have covered elliptic integrals. It can happen. So here's your first exposure to it. And if you want to learn more about these, I recommend that you consult a textbook like Mary Boas, because she has a good section, some problems on this. How do you solve these guys? Well, you got to do it numerically. Or if you're a real Luddite, you can look it up in tables in an old dusty book somewhere. But anyway, that's the solution to that is the magnetic vector potential due to a current carrying ring. And that is at any point in space, not just on the z-axis. It is possible now that we have an expression for the magnetic vector potential to go ahead and calculate the magnetic field from that, which I will do that in a forthcoming lecture in, well, I'll stick it in with the BOS of our law part 2 lecture, okay? Leave this up here for a minute more before I wipe it away. Third and final example I'm going to work through is that of the magnetic vector potential due to a sphere that bears a surface charge density sigma and is rotating with angular velocity omega. As always, the radius of the sphere is capital R. And your first inclination might be to align omega along the z-axis. As it turns out, it's actually far more convenient in terms of integration if you rotate it such that omega is at an angle psi, and the radius, the field point or observation vector, is along the z-axis. So we'll write omega is equal to omega sine psi in the x direction plus omega cosine psi in the z direction. Now the source vector is just going to be r sine theta prime cosine phi prime x direction plus r sine theta prime cosine sine phi prime y direction and r cosine theta prime in the z direction. Magnitude separation vector can be found readily. By the way, Griffiths has this problem worked out in his textbook, but I do like how he sets it up, so I'm basically just going to walk through his example. Okay, so the magnitude separation vector, if I can make use of the trigonometric identity a couple of times, the cosine squared plus sine squared is equal to 1. Ultimately, I will wind up with r squared minus 2r cosine theta prime plus r squared. Before I can evaluate the integral, I need to write down an expression for the surface current density. That's just equal to the surface charge density times the velocity. And velocity is equal to the cross product of the angular velocity and the source vector. In the x direction, we have minus omega r sine theta prime sine phi prime cosine psi. And finally, in the z direction, we only have one term. Okay, so you'll notice that in all of these terms except for one, you have a sine phi or a cosine phi. Now, in the denominator, the magnitude of the separation vector, there's no phi. When I integrate this over the surface area of the sphere, all these sine phi, cosine phi terms are just going to drop out. They contribute nothing. So you integrate sine phi from 0 to 2 pi or cosine phi from 0 to 2 pi, that's just equal to 0. So these go to 0 upon integration. Left with just a single term pointing in the y direction. So combine all these together. And actually, I could have pulled the sine psi out as well. Anyway, the point of here is that when I integrate from 0 to 2 pi, what happens is I'll just integrate, I'll gain a factor of 2 pi. And this is equal to minus sigma over times omega r sine mu naught over 2 in the y direction. And I think I wrote right sine theta prime here. And we also have an additional factor of r squared, because remember, when you integrate over the surface area of a sphere or in spherical coordinates, it's going to be r squared raised to the sphere squared times d theta sine theta times d phi. So make sure I didn't lose track of anything here. No, I did not. Here you want to make a change of variables. So we'll set u equals to cosine theta prime, and consequently du will be equal to minus sine theta prime d theta prime. And as a result, the limits of integration will change, will go from 1 to minus 1, but because of this minus sign, we flip it around. So the upshot of it, and unfortunately I'm going to have to erase, this. This stage of the game, it's useful to have a table of integrals on hand, so you don't actually have to spend a bunch of time working out the integral. And this is equal to